Hello and welcome to the third session of our drone workshop. Today we will talk about drop simulation or drop test and try to investigate how, for example, a rough landing maneuver will have influence on the stability of our drone. And yes, before we start to dive into this very interesting topic, I would just like to check if audio is working fine for all of you. So please raise your hands. Yes, that looks good. In the case you cannot hear me, or you have problems with the audio maybe, you can also try to use our toll-free phone dial, and there are several numbers provided in the email you got after the registration. Great. Then let's start. Maybe it's more retrospective at this point. We started 2 weeks ago with our first session about aerodynamics, and yes, there we investigated how a drone or how the propeller of the drone is creating lift. And there we also, during the homework, checked 2 different designs and how a small design change can improve the lift force generated by the drone. Last week we were talking about structural design and structural simulation, and a lot of you have submitted the homework, so I think you really got a deep understanding for how to test parts on a structural behavior, what's the difference between simulating or investigating a single part or a assembly of several parts using contacts. And today we will perform a kind of crash test of a drone while landing and investigate therefore different, let's say, crash speeds or landing speeds. And next week, as our final session, we will take a look at vibrations, which are, for example, created by the engine and which can have a negative effect on the flight stability of the drone. Yes, let's take a brief look at our today's agenda. So we will start, as you know, with some fundamentals about a drop test. This will be especially about the difference between a drop test and a real crash test, and we'll also talk a little bit about which strategy we are following to model this drop. Then we will together set up a simulation, which is, by the way, equivalent to your level 1 homework for the session. We'll do some result interpretation, and later on I will present the homework assignment to you, and we will have some time for question and answers. Yes, I think most of you know me, therefore we'll try to keep this my introduction and all the other introductory stuff quite crisp. Yes, my name is Milad. I'm working at SimScale as academic program manager, so our aim is to make SimScale the best place for students and professionals to learn and do engineering simulation. I have a mechanical engineering background with majors also in simulation, so I have a lot of experience in simulation and try to share this with you during this workshop series. Again, what is this workshop about? So our aim is to give you guys a quick introduction, a very hands-on introduction into engineering simulation, and bring this both worlds together, the world of drones and drone design and the world of simulation. Therefore, this workshop is not a, let's say, fundamental training on simulation theory or simulation application, but as you know, with submitting all 4 homeworks, you can qualify for a free professional training with a value of €500, which is really a fundamental training about simulating or doing engineering simulation with SimScale. If you're interested, for example, in simulation theory and are your students, there are a lot of quite good books I can recommend to you, and I'm quite sure if you're studying engineering or something similar that there will be a good lecture or course about this. And we are, offering this workshop because we want to introduce interested engineers and interested individuals to engineering simulation and to SimScale. And for sure, we would love to get product feedback from you and other contributions. A lot of you are active on the forum, and there are also some people asked if it's possible to do simulations of your own design, and yes, you would really appreciate this. So if you want to modify a simulation, maybe make it more complex, more detailed, or simulate your own design, please feel free to share all your thoughts and also problems on the forum, and we will try to to help everyone. And if you are interested later on, we would also love to put your simulation project into our public simulation library on simscale.com/library. So this is, as I mentioned, the third out of 4 1-hour online lessons with a live demo. I will show you the fundamentals of this drop test today. Later on, I will present a homework assignment to you, which you should do or can do for first of all deepen your knowledge which you gained during this session, and also to qualify for this free professional training, or also for certification which you can use for your resume later on. And when you do have made the homework, just share it using the form which you can find on the SimScale website, simscale.com/drones. And again, some questions. I know we talked about them the last sessions, but they are asked again and again. So yes, this workshop will be recorded. You should not start to simulate during the workshop. I think it makes more sense to have the full attendance on the workshop, and later on you have more than 1 week to do the simulation. You can simulate for sure, and you should simulate for sure yourself. All of you which are here in the session have been provided with the free professional access during the workshop time to use all the functionalities of SimScale without limitations. If you're academic, you can use it every time for free. And if you need help or something like that, if you have problems, just use our forum, you will get the free support. And yes, if you want to learn even more about simulation, you should qualify for professional training. And additionally, you can also check our simulation library and other tutorials where we're providing a lot of resources to get started with other simulation types or other simulation projects. Yes, and again, I want to say thank to all of you for submitting so much different homework assignments and being so active on the forum. It's really a glad motivation for us guys here at SimScale to see that you have so much fun with this workshop, and that you really learned a lot in this short period of time. And today we will also take a look at the homework of last week, just maybe to make a little more vivid what also can be learned doing this homework. And therefore I've prepared some images. And these are images of the second level of the last homework assignment. And let's start here. This is an image showing on the left side the simulation result for the coarse mesh, and the right side was a more refined mesh. And on the first view, it looks quite similar, but if you take a deeper look, you can really see that, for example, here in the area of the screws, or here where the arm is, there are some differences. And if we, for example, now take a look at the result for higher forces, so this is 1.5 Newton, 2.25 Newton, 3 Newton, you can really see that this has an impact. So we have a small change in the arm because the lift force, which is here, is changing. But still there is a difference between the simulations, seem not to be related to the forces. And by the way, for sure, left and right side is the same, absolutely same simulation setup. And the reason is really the mesh refinement. So if we will take a look at a detailed look, for example, here, we have the coarser mesh and then the finer mesh, and you can really see how the mesh refinement changes the result. And this is something we call mesh independency. So we're looking for a mesh independent solution, and that means that it's a little bit like the iterations we are using. Making the mesh finer will increase the precision of the result, but there will be a point where a mesh refinement will not have any more significant impact on the simulation result. Exactly for this kinds of mesh we are looking. And the standard process there is really to start with, let's say, coarser mesh, and then to refine it everywhere where we see, for example, high stresses. And you can really see that there where we see there is a high stress, there is also the change when the mesh gets refined. And so this so-called mesh-independent solution is in the end, yes, what we are looking for. And in this case, for example, the difference will not be so big. So I think you can still use, for example, the coarser mesh for a first design decision. But the process should really be, and if you want to use simulation later for your own project, start with a little bit coarser mesh and refine it everywhere where you expect or where you see high stresses after the first simulation. And for example, here, if we take a look at the screws, that's really a big difference. And it's also, if you think about it, it makes sense why there's a difference. Let me therefore open my sketchboard and just for a kind of let's say experiment, or just a little bit, think a little bit about it. Just imagine we would have here a graph, for example. Here we have a y-axis and x-axis, and on this y-axis we're taking a look at the stress sigma, and here we will take a look at the coordinate. And let's just say we have or the stress acting like this. If you would take a look at the analytic solution, or how it is really. And then if we would start to mesh, for example, with the coarse mesh, and we would put nodes here, then this peak would be ignored. So then we would have this kind of result from a simulation. And therefore, but if we would put here 2 additional nodes, the result will become much better. And that's the reason why you have to put or have a finer mesh where you have, for example, high stress, because everywhere where you have a high gradient, a high change, for example, here at the bolt, you should apply a finer mesh. And there's already a first question by Awad. He wants to know how can we find out about this mesh independency. And for sure, experience is very important. But if you have no idea, start with, as I mentioned, is a coarser mesh and refine it more and more. Okay, yes, that was our small retrospective on the homework. And then let's now dive into our today's session about drop testing. And before we start to set up the simulation, let's discuss a little bit again the fundamentals. And there is a big difference between a drop test, let's say, and a real crash test. And this is very important to, or this is important to understand this. If you really want to simulate drop tests with FEA simulations. And let's make a very easy example. Just imagine you have this car here. I know it's not very nice, but I hope that you guys will understand what it should show. And this car will impact the wall. If we have a really high speed, and high speed I mean for a car, let's say 30 kilometers per hour, then the car will really get destroyed. And then this crash test, by the way, is about finding out what happens inside the car to protect, for example, the passengers. And this is something quite complex, which is not possible to cover with the simulation type we will use it in the next session. But if the speed is lower, so let me visualize maybe a little bit again. For high speed, as I mentioned, our car will be, the front of our car will maybe looking like this. And then we have plastic deformation and cracking, etc. That cannot be covered. But if we have a very low speed, and maybe some of you now knew that there is a kind of law that up to, I think, 3 kilometers per hour, when you have a very really, let's say, small impact, that then the cars should not be destroyed, the front bumper. And this is because that with this high speeds and this high energies, we have only elastic deformation. And nothing will crack, nothing will be destroyed later on, and this is something we can simulate. So this drop testing we're using in the end, it's only suitable if you want to investigate, let's say, small forces or small stresses, or let's say another one, stresses and forces which are not big enough to have a really destroying impact on this material. And therefore, this kind of simulation is really suitable for our drone testing because we want to test which is possible till the drone gets damaged. And so therefore, it's another way of setting up the simulation. I think you all can remember when we did the simulation of the drone, of the drone arm. Then it was like, let's say it's again a very simplified sketch. What we fixed the drone here. In order that it's not moving when we're acting the force. And that was the reason why the drone, if we wouldn't have this boundary condition for fixation, it would just fly, because there is this old physical law that force is acceleration multiplied with mass. And what we will do right now, it's the approach now, we will say, okay, we'll remove this fixation and also remove the external force, and then it will drop down. And we then have a floor. Then we can simulate this drop. And here in the end, it's really, again, very easy fundamentals of mechanics, because this is the floor and this is our drone. Then, in the end, the energy of the impact is only depending on the mass of the drone and on this distance here. Let's call it d. Because, as you know, the force here, which is pushing the drone down, this is, or can be defined as F is the mass of the drone multiplied with the gravity, and the energy, therefore, is the mass of the drone multiplied with the energy, with the gravity multiplied with the distance. And it's even possible to calculate out of this energy a velocity and the other way around. And what we will do in the end to simulate this drop is we'll set up a simulation, a FEA simulation, not fix this drone, and just define a contact between the underside of the drone and the floor. This sounds maybe a little bit abstract, but I'm quite sure when we will do the simulation setup right now, it will become more vivid. Then, yes, let's start. The procedure is again the same like last time. We will upload a CAD model, then prepare the simulation. So we'll create a mesh based on the CAD model, make a simulation setup, define material properties, boundary condition, etc. And then we will get a result which can help us, for example, to have a design decision. And yes, the demonstration, for the demonstration today, I will use the same model which will be part of your homework. This is in the end level 1 homework I'm presenting to you right now, I'm demonstrating for you right now. And it's a little bit similar to last time. We will start with a simplified model. So in this case, I've fused all parts of the drone except the battery to one part. So this also has to be out of one material, which is for sure not very realistic, but it's a good beginning. And we have the battery. No bolts, no screw connections, etc. And we will do a drop test with this simplified drone model for 4 different, or at your homework we'll do it for 4 different falling speeds, and today we'll do it just for one fall velocity. Yes, and first of all we have to do the CAD upload and create our mesh. And you will be provided later on for sure again with 2 step-by-step tutorials and related links to import the project, which includes the geometry to your workspace. I will here just create a new project from scratch. And upload a geometry. And here we can choose what kind of file we want to use. Okay, and now the file is proceeded to SimScale, and we can start with the meshing. And just to check if everything went right, we can here check the bounding box length makes sense, so the scale is right. We have 3 solids, what we wanted, and by the way, 251 different surfaces. Now we want to create the mesh, so we'll create a new meshing project. Just use a default name. You can choose in the input the name, whatever name you want, but if you are doing a bigger project, I would really recommend to use sensible names. And then we will add, first of all, we have to select the base. So we will make the simulation based off this CAD model, or the mesh based on this CAD model. Then we have to add a mesh operation. We will again use tetralization with refinements. And first of all, we have to define this range for the base mesh size. And this will be 1 millimeter. And the smallest will be 0.003 millimeters. Then we will use the first order mesh. Some of you had problems with meshing because they use second order mesh. And really, again, please use first order mesh to second order mesh. Sometimes needed more preparation and some more manual settings for meshing. And the rest is good. We will take 8 cores to accelerate the mesh computational process later on. Just save, and now we can start to add mesh refinements. And here we need 2 mesh refinements in the end. First of all, we will add a mesh refinement to say surfaces or to areas where we expect to have later on high stresses. So let's call this high stress zones. And there we will have a much finer mesh, starting with 0.0003 millimeters up to 0.0001 millimeter. We will use a moderate refinement, so this is about how it refining between in this range. And now we have to assign it, and we will assign it to faces. So for visual pickup, make sure that you have this right selection mode, and we will apply it where we know we can expect high stresses. So here at the arm, at the side, for example, or also here, because here we will have a high bending of the arm, and for sure here, because here the drone will, while the drop test, touch the floor, which is, by the way, also part of this model, because we need a floor somewhere to where it can touch. Yes, great. And now just add selection from viewer. You can also select it manually, click the save button, and the refinement zone is created. Next, we will create a refinement which will make our mesh coarser. And that sounds strange, but it's important because we're not interested what happens on the floor. Therefore, we shouldn't put too much effort in it. We will later on assume or define material properties for the floor where we know there will be no deformation, etc. So we can really use a coarse mesh. And so we will, from 1 meter to 10 centimeter, very coarse for refinement parameter, and here apply it to the whole volume. And now we're done with our mesh. We just have to start the meshing operation, and the mesh will be created automatically. And we'll get notified. Let me delete the old meshing jobs which are still here. And now we can see our meshing job is just in the queue right now, and will be notified when it's done by email and also in this progress bar. Okay, let's do again a quick wrap up. What did we learn? I again showed you how to output a CAD model, in this case a step file, and then we created, after we checked the CAD model if everything is right, created a tab mesh with refinement. And yes, again, I talked about a little bit about how important it is in this case, or as a beginner, to use first order meshes. And then, yes, we used some refinement options for making the high stress areas better resolved and making or creating a coarser mesh on the floor. And 2 topics we did not talk about today, or cannot talk because time is somehow limited, is CAD cleaning, preparation, and mesh quality. So when we're talking about cat cleaning, what we actually mean is that if you look here, this engine is really simplified, for example. By the homework level 2, the engine will be more detailed, but here, also because we had to fuse everything, it's in the end just dummy for the engine. And in the end, cat simplification is more about, and preparation is, for example, splitting surfaces if you want to define a contact later on, and remove unneeded features. And this is also a very important part. So your simulation actually starts with your CAD model, or with the preparation of your CAD model. And once this mesh is created, we will also talk about, or we'll also see the mesh quality, or see the mesh, and there are also some criteria for mesh quality, and this is also something which we will not talk a lot about it. If you're interested in this, in the last session we talked a little bit more in detail about this issue with mesh quality. Okay, our mesh, by the way, just started to be computed, and since I know that this can take some time, I for sure prepared a simulation. Let's just delete the prepared project, the simulation prepared project, and continue from this point on. So this is, by the way, exactly the same mesh, the same settings. And you can see we have here this coarse mesh where we need it, and here the mesh was refined everywhere where we added this refinement option, especially here, for example, or here. And now the next step is really the actual simulation setup, so therefore we will switch to Simulation Designer and create a new simulation and give it just a name like drop test. And here right now we have to choose what kind of analysis we want to do. And since we are now really looking at the transient phenomenon, at something that is moving, we cannot use static analysis anymore. We'll use dynamic analysis with advanced options to have also additional boundary conditions, and what is most important, for the contact definition. Great. Next, we will choose the mesh for the simulation we want to use, and we will use for sure the mesh we just created. Then the mesh will also be updated, and you can see it in the 3D window. And first of all, we'll start to define contact. And again, maybe it's a little bit retrospective to the last session, but let me just explain you in very crisp what the contact is and what the difference between a contact and a physical contact again. Okay, since we are here simulating assembly, I mean, the drone is out of two parts, and we have the floor, but it's still assembly. And we have to define how these parts are connected to each other. Because for SimScale, or for the solver and the tools which are working behind SimScale, they don't know about it. It could also be that these parts are independent and not connected. And physical contacts are just to define kinematic relationships of parts, while the physical contexts also take in account other physical stuff like forces and stresses, and how these parts are mechanically interacting. And here we just need one physical contact, because there are just two parts connected. It's the battery and the drone frame. So let's create a contact. Let's call it battery to frame. We will for sure use a bounded contact because it's a planar faces. And then we have to choose which is the master and which is slave entity. The master entity in our case will be the backside of the battery, or the lower side of the battery. And here graphical selection makes a lot of sense. So and for graphical selection, it's very helpful sometimes to hide other parts. So here we'll select this face, add it as a master. And now we will do the same thing. Let's just clear the selection with the slave, and this is for sure this face of the drone frame. And this is, by the way, what I'm referring to when I was talking preparing the CAD model, because this surface was splitted to have a perfect contact patch here. Okay, but now I just added both from the viewer, and now clicking the save button created the contact finally. Yes. Before we start to define physical context, we have first to take a look at the model. So in this part of this, we call this, by the way, the project tree, is about which physical models should be used in general. And first of all, we are expecting nonlinearities, so we'll activate this nonlinear option, and then we have to define gravity. Some of you might ask why we don't define gravity for the last simulation. The answer is that in this time we have not an external force, but the force in the end which is applied on the model is applied indirectly by the fact that this model is moving and impacting on a plate, and therefore gravity has a big influence, and we have to define it. So we define the value 9.81, and then the direction. This should be the -1 direction. So just put -1 here. And now the model definition is done. Yes. Next, we have now defined how these parts are connected to another and what's the physical environment, how it's looking like. But we have still to define how these parts will interact later on. And this is a physical contact. So we'll now create a physical contact which defines that these parts, if they are touching, that it's then really impact, and then we have a physical reaction, physical or reaction force. So let's start. First of all, we have to define general settings for physical contacts. We will use augmented Lagrange as the solution method, and for nonlinearity resolution, the Newton approach. So this is a approach for solving nonlinear equations. And you don't have to think so much about, just use the settings and save. And then we can add the one and only contact we need right now. So when we click here on add contact, the new contact will be added to the project tree. We'll give it a name, in this case drone to floor. We'll use a frictionless augmented Lagrange contact. Frictionless makes the computation quite easier and simulation more stable. And since friction will not have a very, very big impact on the results, it's better to somehow easier to use this option. And now we have to define again master and slave. And the difference to standard contacts, physical contacts, they're very sensitive regarding what is master and slave. And you should keep in mind that with every iteration, so with every step this part is moving, the solver tries to find a connection between the master and the slave. So you should choose this surface as a master which will move less, and in this case it will be the floor, which will not move at all. So we will select here the floor, add it as a master, and slave phases, because I think the contact will be first here and here, we will use these two phases. Now we have the second contact, and now we have to define the materials which we want to use. And this is quite similar to the last time, but let's do it again. So let's start with the ABS material. This is the polymer which this drone is made of. We would say we would print this frame with a 3D printer. For sure the engine is not made of ABS, but this is a simplification we made for this first step. Later on, level 2, you will use a more complex model where you have the engine as the parts, the battery, we also have screws, etc. And the Young's module of ABS is for sure different. So let's type in the Young's module. The Poisson ratio is 0.35. We have no damping, no creep. And we have a density of 1040. Last but not least, we have to assign it to a part, and so let's select graphically. You have to change the selection mode for this. The frame, add selection from viewer, save. All first materials defined. Next, we will define the material for the battery. For sure, the battery is made of different components with different materials, but from our experience, because we're not interested in the battery but on the frame or on the whole behavior, we will assume this battery as a homogeneous material, and based on the density let's say on the volume and the mass of the battery, we have just calculated some material values. So the Young's module is if you enter it, then the Poisson's ratio is 0.34, and the density is much higher than ABS. It's 2500. Again, we have to choose the part we want to apply it on, the battery, and material choose defined. Last but not least, we need to define a material for the floor. We will use steel, because I know it's again a simplification, but it's also important to have a kind of reference. For this, really, let's say a steel grounded thing is quite good. So, and here we will use now our material library because steel is already existing. Just click on save, and now everything's updated, even the name. We just have to choose the volume we want to apply it to. In this case, it's a floor, and now it's defined. Well, and now we'll on the end of the simulation setup, and what we're defining now is quite important. So we go to the initial conditions, and initial conditions you have to think it's, or you have to keep in mind, it's really like what are the values. Here you can define the physical values at the beginning of the simulation. And since we want to simulate with different falling speeds or falling velocities, one strategy would be to change the height, but then we would need 8 different meshes. And therefore we will just apply a velocity on the drone. And then we have to change on subdomain based. And we save it here. Now we can add on a subdomain of this model of the mesh for the beginning a velocity. And let's call it just here. Fall velocity, for example. Then we have to, let's say, minus 2 meters per second. And then just select where we want to apply this. And for sure not on the floor, because the floor should not move. Yes, then under the initial condition we don't have to touch. And what is now missing are the boundary conditions. And here we only have constraint boundary conditions because we have no external load. And we will just use them to define, first of all, to fix the floor plate, and then to define the symmetry because we are using a quarter model. So let's start with the first one for the floor. And the floor should not move, it should be the floor, and therefore we have to add this fixed support boundary condition. We'll add it on the surface here. And now the floor is fixed. Next thing is we will define boundary conditions for symmetry. We have a symmetry plane here and here. And instead of using the symmetry plane boundary condition, we will use or set up this boundary condition manual, because for such large models, or in general, it's more stable. The symmetry plane boundary condition can cause some problems, and we want to be on the safe side this time. So we will use herefore we will start with the XY symmetry plane. So let's give it a name. Take a look at the physical meaning. For this XY plane, it means that the parts cannot move in X and Y direction, but in Z direction. So we will have for this one constraint, and Z direction is prescribed with a value of 0. And then I've changed to faces because we want to assign it to faces, and then we will just choose all faces here, which are on this plane, even the floor. Just save. Forget to add them again. You have to be sure to save everything. Okay, now only one is missing, the symmetry for the YZ plane. It's the same, and then it's the same, but the only difference is this time Y and Z are unconstrained. Again, we have to choose here faces. Yes, and now we have all boundary conditions, and actually 2 things are missing. First of all, for this simulation, unfortunately, we have to touch the numerics. So for those of you who are not very familiar with mathematics, numerics means that say there we're defining which tools and algorithms we want to use to solve these equations. And this kind of simulation is let's say, quite sensitive, so we have to use special settings. We will start with time integration. We will change it to Hilbert-Hughes-Taylor, HHT. And this is important, you can imagine, because we have now a real time, not a pseudo time anymore. And the convergence criteria, we will set it up to E minus 5, because for transient simulations or dynamic simulations, we will need a lower tolerance. Just save it. Yes, and now we can start with simulation control. And here is again a big difference to static simulations. As I mentioned, we are not talking about a pseudo time here, we are talking about a real time. And therefore, we have really to think about the time step, because every time step makes our simulation bigger, a simulation result, and will increase the time we need to solve the simulation, to compute the result. And again, I will need to use my sketchboard to explain why this is very important. Just imagine, we have our drone here, and let's say we applied a fall speed of 2 meters per second. And then there is our floor, and the distance between the floor and the drone, d, is, by the way, 0.1 meter about. And now, I mean, and this is again similar to the mesh, because you only need to find mesh there where you have a change, a gradient. And until this, the first face of the drone will touch the floor, there will be no real change of quantities on the drone. Stress, etc., will not really change. Therefore, we can have a very, very coarse time discretization, very large time steps until it hits the wall. And if we want to be think economically, the best would be to have a big time step just before the moment it hits, and then have a time step to really resolve all dynamical changes. If we now take a look at the formula or definition for velocity, velocity is defined as distance per time. And therefore, you can say, or you can calculate in the end, that the time till a defined distance is reached can be calculated by defining the distance by the velocity. And in our case, that means, example, we have 0.1 meters divided by 2 meters per second, and this will result in 0.05 seconds. In these times, nothing will happen. So if we are smart, we will have a time step which is coarse before 0.5 seconds, then becomes small. And that is what we are doing here, or we will do right now. First of all, we have to change the time step definition from manual to auto. And then we have to define a simulation interval, so which time interval we want to simulate. In this case, or we will for all periods give you these values, and we also can, if we click here, because here you're defining the time step length, but clicking on the symbol allows you to use a table where you can define different time step lengths for different absolute time. And then you can just upload a CSV file which is describing how the time step should change. And this file will be provided by us for all tutorials. So let's call it time 10 meters, 2 meters per second. And then we can just choose this file, upload it. Then you can see till 0.045 seconds, the time step will be 100th a second, and from then on to 0.055 seconds, which must, by the way, be the same value like simulation interval, we will have a quite smaller time step. Just apply this. We'll increase the maximum runtime to nearly 3 hours and use 16 processors. to calculate the solution. Last, we can, for example, add an additional solution field. So we will here just add something, the von Mises stress. And we can also we can add an area calculation. So we can, for example, pick the surface here. It's a parallel tip, and calculate the minimum and maximum magnitude of the displacement to have a plot, for example. Then just sign. And now we can create a new run. Let's just rename it. So let's call it 1 2 meter per second. And start the simulation. In your homework, you will do this for 1, 2, 5, and 10 meters per second, but we will get, as I mentioned, a step-by-step tutorial, and as well the CSV files and all the resources you need. And yes, the simulation will take some time, up to 1 to 2 hours. So we will use for the post-processing a prepared result, but let's just make a small wrap-up. We just discussed now this general simulation setup for dynamic simulations. Especially, we talked again about contacts, difference between physical and let's say numerical contracts. We defined several materials, defined boundary and initial conditions, added some solution fields as well as result control items. So we added von Mises stress, that is calculated as a result field, and we had a kind of calculation or tracking of the displacement of the propeller tip and start the simulation. And one topic here would be so-called numerical solver settings. So just what we did right now with changing the way of time discretization and tolerance can be doing quite more, let's say, high level. So this is nothing you should care about. It's really then for very experienced notes with a theoretical background. And there are for sure other possibilities of solver control. So to have this time steps even with more different let's say areas where we have not only 2 different time step lengths. Our simulation would take time, so therefore I prepared everything. Once the simulation is finished, you will get notification, and you can see then here residuals, and we can switch to post-processor, and for example take a look here at the result field. And the post-processing for this kind of simulation is just a little bit different. First of all, we have to wait till the simulation is loaded completely. This is done right now, I think. Yes. And here, because we want to see how it's moved, we have to add first of all a wrap by vector filter, which will choose here as the option displacement, and that means that this filter right now will visualize the displacement field of the mesh of the model, and this includes the deformation as well, how it's moving. And for example, if you now change the time step, so just imagine this is 0.1 second, you can see that it's fault a little bit, and then we just take a look therefore at this, and now we can, for example, also add a field which we want to visualize the stress. And if you jump to the later step, then we can see, then for example, we can visualize how this is moving, but we'll do it right now locally because I've downloaded the results. Just because this is, then we can create animation. Create the same simulation and downloaded it and extracted it on my desktop, then you can just read it in. And then I created the same filter, and now here we can just create animation and let it play through, and then you can really see how it's falling, then the stress is not changing, because there's no change of values, therefore we can have this bigger time step. And now a time step is 0.01 seconds. And from here on, time step becomes quite smaller. Just imagine one step here is 0.0002 seconds. So in reality, this is a very fast process. You can really see how now the stress is distributed through this to the drone, and it's even jumping a little bit off. Okay, great. Then this was the demonstration. For the wrap-up, I showed how to create this surface result plot and visualize the deformation. There are a lot of other things you can do. For the post-processing, you should also take a look at the step-by-step tutorial of last session. Maybe you can get some inspiration there. I would really appreciate to see your own ideas. And what we could do as advanced things would be to derivate additional physical quantities, like for example relative stress based on the maximum stress which is allowed for the material, and for sure it's also possible later on to take a look at the plots we just created with this result function item. Yes, finally, let me just present you your homework assignment. Your homework assignment will be about performing such a drop test yourself. First of all, on level 1 you will do the same simulation I just showed to you, but for 4 different velocities of fall velocities. And on level 2, this is a little bit similar to the last workshop. We will use some more complex assembly where you have your own solid for the engine, your own solid for the propeller, your own solid for the chassis, your own solid for the screws, your own solid for the battery, and then we'll investigate what is also 4 different fall speeds. Starting from tomorrow, I think, you can access on our website, or we will open this third tab where you can access a recording, where you can import the project to your workspace, and also access the, again, step-by-step tutorials. If you need help or have questions, please use our forum. And yes, it's a little bit more, not difficult, but a little bit more steps than the last homework, but the results are really awesome. And if someone of you wants to modify something, just feel free. We would love to see your own ideas. And I would really like to encourage you to also to realize your own simulation ideas and product ideas using SimScale. Yes, then thank you very much. I really enjoyed the session. I will see you, and I'm really looking forward to all your homework submissions, to your questions, to our discussions on the forum, and for sure to see you next week for our last session. Thank you very, very much from me and the whole SimScale team. Warm greetings from Germany. Have a nice evening, and see you next week. Bye.